broadcast.
Okay.
Oh, you did that.
I did it.
Wow, very efficient.
So we'll give it a few minutes before we get started. Let people sign on.
Mm-hmm. And get a coffee. You should start 11:05, American standard.
Right. No, MIT standards. Uh-huh. Okay, should we get going, Kong?
Sure. I thought you want to wait until 11:05, but it's okay. Okay. Just give me a minute. What should? 1 minute. 1 minute. Okay. Hi. Greetings, everyone. Welcome to our Zoomina series again. Nice to see you on Wednesday. So I'm just doing like a usual update that I usually do every week. So first thing is that if you are interested in getting like news or announcement for our future Zoomina series, like feel free to subscribe to our mailing list. This is like our official way of distributing the announcements to the public. And if you're interested to know who our past speakers are, if you're interested to listen to their previously recorded sessions, feel free to go to our group website where all the recorded sessions will be, they're actually uploaded. I try to update this very, very frequently. And then like in addition to that, so after the speaker's talk, there's also a Q&A. I actually uploaded all the Q&A questions to the Dropbox folder that you can find also in our group website. So you can look at the past Q&A questions if you want. And if this is your first time here, if you want to ask a question during the talk, feel free to type your questions like on the Q&A function, like anytime during the talk or after the talk. And if you're not familiar with the Q&A function, you still can raise your hand if you're new or you're not familiar or your question is too long. I mean, the last thing is that try not to use your chat because like I think there have been some instances of Zoom bombing on the chat room. Depending on the situation, I might perhaps not allow anyone to type in the chat room. So I will actually I will copy and paste this in the chat room that you can, so that everyone can see. So I will now pass the session to Bob so that he can introduce our speakers today.
Okay, so today we have two excellent talks, materials-oriented talks. The first one is by Nobuhiro Yanai, I believe is the way you pronounce it, maybe not.
Right, it's correct.
His talk is on material chemistry of triplet DNP, in which he will be using triplet state, photoexcited triplet states to generate high polarizations. And the second is Frederick Blanc, who's from the University of Liverpool. And later on in the program today, he'll be telling us about zeolites as heterogeneous catalysts with some studies with DNP. Okay, so Nobu, you want to take the virtual platform and tell us about triplet state DNP.
Okay. So can you see the slide now?
Yeah, we can still see the slide. Maybe you want to like press escape so that.
Do you see the still program?
We can only see like.
You're still getting that black part.
Yeah, exactly. Yes. The Zoom.
Okay, let me try it again.
There.
How about now?
Yes, it's perfect now. It's good.
Okay. Okay. So, okay. So I actually unclicked that that optimization one. So okay. Anyway, so hello everyone, and thank you for your kind introduction. And I'm Nobu Yanai. My first name is a bit too long, so you can call me Nobu. And I'm in Kyushu, Japan. So it's 12 a.m. in Japan, so kind of midnight. So yeah, but I'll try my best. Okay, so, and first of all, I'd like to thank Ko and Bob to invite me to this great Zoomina series. This is a really nice series. And also I want to, they acknowledge to hold this magnetic resonance community, because actually I'm the material chemist, more like synthetic chemist, and my background have nothing to do with the magnetic resonance, but actually we started this project 4 years ago, but since then this community is quite open to like newcomer like me, and I could have a chance to talk to you guys and also give a presentation in conferences. So I really appreciate that. So, and also, of course, I want to thank to my great lab members. And so they are my group members and they are very happy to be hyperpolarized. And these people in blue color contribute a lot to this project. And also I want to thank to my funding support from JST Presto, Quantum Biology Project, and also to my great collaborators, Dr. Uesaka and Dr. Tateishi in RIKEN for their help of the measurements, Triplet DNP measurements, and also Dr. Kurashige for his theoretical support. Okay, so I think most of you are more very familiar, much more familiar than me about the problem of NMR and MRI. That's the poor sensitivity. So, so that the hyperpolarization is a very good method to improve the sensitivity for the protein in cell NMR and MRI, and to increase the polarization. And DNP using the radical is one of the most powerful methods to do that. And by just decreasing the temperature, you can achieve the high polarization of electron, and you can transfer that to various nuclear spins. And if you cool down the sample to like down to the 1 Kelvin, you can get very high polarization. And it's useful for the mass NMR and also for the dissolution DNP. So, you know, well that it's now very successful on the clinical trials for cancer imaging. So you can hyperpolarize at 1 Kelvin and transfer polarization from electron to nuclear spins, and then you can dissolve to observe in MRI. So it's great technique, but I think most of you would agree that there are still challenges. Like you need a very low temperature, around 1 Kelvin, to achieve this high polarization. And also the targets are still limited to the specific compounds with the long relaxation time. Otherwise, you cannot see it. So especially, we need to tackle this temperature problem. So instead of low temperature DNP, if you can achieve the very efficient room temperature DNP, we can dream to achieve the cheap and compact dissolution DNP for maybe more widespread use, like maybe you can install into the local hospitals, small hospitals. And also, maybe you can do the continuous DNP and also eventually DNP in vivo. That's a kind of dream. And you know that there are a few techniques to do this room temperature DNP, like using parahydrogen or Saber or NV Center and Oberhauser. But today I want to focus on the one of the specific technique, that is the Triplet DNP. So the Triplet DNP is the DNP using the photo-excited triplet electrons. And actually the first example of room temperature Triplet DNP with the enhancement over 5,000 high enhancement was achieved by Vancouver and coworkers in 1990. So, and since after that, several groups joined this Triplet DNP, and they did a lot of studies. So they basically optimized the experimental conditions, like conditions of the sample or laser and microwave. And then the Takeda and coworkers eventually achieved the very high polarization of 70% at 105 Kelvin. And their systematic study was nicely summarized in his book. And also, our collaborator Tateishi and coworkers reported a very high polarization of 34% at room temperature. So now you can achieve very high polarization even at room temperatures. That's great. So next, let me explain about the mechanism of and more detail about the technique. So now you have the polarizing agent doped in the solid crystal, and you shine the light, and the electron spin polarization is produced as a photoexcited triplet state, and this polarization is transferred to the nuclear spin by the integrated solid effect, and you repeat it. Shine the laser, shine the microwave, shine the laser, and shine the microwave. Then you populate the spin polarization in the bulk at room temperature. So obviously, the biggest advantage of Triplet DNP is that you can make the very large polarization, like over 70%, even at room temperature, by using the non-equilibrium polarized state of the triplet. So pentasine is the most common polarizing agent, and pentasine absorbs the light and undergoes the intersystem crossing, and this efficiency is about 60% or so. And this intersystem crossing is actually the spin selective. So you can automatically get the high polarization of over 70% at room temperature. So besides this large polarization, the pentasine have a good feature of the long polarization lifetime over like 20 microseconds. So you have enough time to transfer the polarization to the nuclear spins. But actually, this is not like very long, right? Like it's microseconds, so you should be quick. So you need to very efficiently transfer the polarization by satisfying the Hartmann-Hahn condition, and so that you can coherently transfer the polarization from electron to nuclear spins. But the problem is that the EPR spectrum of the triplet is too broad. It's like a few hundreds of megahertz, and it's much bigger than the proton Raman frequency at the same magnetic field. It's about 15 megahertz. So so that you can only excite, you can only transfer the limited fraction of the electron spins. So to overcome this issue, the Venkaperhers and coworkers introduced the mechanism they call integrated slit effect. So here you need you use the magnetic field sweep, so that you can sweep the triplet EPR spectrum, so that you can let more triplet electron to participate into this polarization transfer process. So here shows the conditions we are using nowadays. It's optimized. So and the setups like shown here, like we shine the laser and the microwave from the opposite direction to the sample here in the actually microwave resonator. So our laser is a bit weird or kind of special laser, having the very long pulse width. It's over 100 nanoseconds, and the pulse is about millijoule per shot. And after the laser, you apply the microwave, and it's the microwave width is like for like 10 microseconds. It's short time and 10 watt or so. And then during that, we apply the field sweep. And this repetition rate is about 1 kilohertz, and to the accumulated spin polarization. Okay, so this triplet DNP is basically this mechanism is understood, and this condition is well optimized nowadays. And then based on that kind of understanding and very nice control, it's now applied to the physics problem, like as a Newton spin filter. But unfortunately, the application of triplet DNP has been mainly limited to that kind of physics applications. So here we propose to introduce the materials chemistry into the field of the triplet DNP to open the pathway to the biological applications based on triplet DNP. So actually previous works on the triplet DNP, people use the big chunk of the crystal, big single crystal, so that you cannot introduce your target biological compounds into the single crystal. And also you cannot transfer the polarization to your target compounds. So our strategy is very simple. So we want to increase the surface area to allow the polarization transfer. So we introduced the nanocrystals and also nanoporous materials. And our another strategy is that previously pentasine has been only used as a polarizing agent. Pentasine has been only polarizing agent in this triplet DNP. But the pentasine cannot be dissolved in water, or you cannot mix it with the biological samples. So that we developed the first example of the water-soluble polarizing agent. And now we can dope directly into water or biological substances. Okay, so let me start with this nanomaterials part. So our concept is the Triplet DNP nanospace. So we are first polarize the nanoporous material and then transfer to our target compounds. So I should mention that there are many great pioneering works on the dissolution DNP using the nanoporous materials. So we want to extend it to the room temperature Triplet DNP. So then we took one of the important family of nanoporous material, that is the metal organic framework, MOFs. Actually, partly because my background is MOF chemistry. And also MOF is very nice because it's crystalline, all that material, so we expect the long T1. Actually, this one of the very typical, one of the most famous MOF, ZIF8, can give you the T1 of about 30 seconds, and we actually deuterate it, and it can give you now about 1 minute of T1 at room temperature. So then we first try to introduce this commercially available pentacene derivative, but actually it was not introduced. So we could not introduce it. So we synthesized this new pentacene derivative having the carboxylic acid moiety. So actually by the help of the coordination bond formation to the zinc, we could nicely introduce this into the MOF. So in the MOF, pentacene works very well. So you can see the similar zero field splitting parameters to the conventional pentacene doped in paraffinil system. And polarization was also similar. The only difference is that you see a bit shorter polarization lifetime of about 9 microseconds, but still it's long enough. So then we apply the Triplet DNP process, and we could observe the over 50 times of the enhancement at room temperature, and at about 100 times of enhancement at 220 K. It's relevant for the gas absorption. So of course, I should say that this is really still the moderate enhancement. And after publishing this one 2 years ago, we are still struggling to increase this enhancement, and we measured many MOFs to get the longer T1. And also we are now trying to transfer the polarization to the gas molecules. So I hope that I can share more results with you in the near future. And the next system is the nanocrystal, actually dispersing water. So we downsized the conventional bulk crystal into nanocrystals and dispersing water. So our question was like this. So can we do the Triplet DNP of the nanocrystals? And also, can we do the Triplet DNP in water? So previous works has been done only in the solid state. So there have been no work of Triplet DNP in water. So we just tried. So we actually tried several different methods, but actually, finally, this very simple ball milling process worked very well, very simple. So we took the very conventional pentacene doped paratafenil crystals and put them into the aqueous solution of the surfactant CTAB and apply the ball mill and centrifuge to collect the nanocrystal dispersed in water. So nanocrystal is a kind of monodisperse, and size is about 100 nanometer-ish. And it gives the very nice, good, stable dispersion in water, thanks to the high zeta potential of positive 43 millivolt. And this positive sign comes from the positively charged surfactant. So actually surfactant is wrapping the nanocrystal. And the most interesting feature of this nanocrystal is actually the air stability of the triplet state. So you may know that the triplet state, photoexcited triplet, is very sensitive to oxygen. So it can be easily quenched in oxygen, in air. So that you can monitor the the quenching process in the transient absorption of the triplet from T1 to Tn state. And actually this, and we estimate the triplet lifetime. It was actually almost similar between the nanocrystal dispersion and the powders, bulk powder. So this triplet is well protected, even in the form of the nanocrystal. This is due to the dense paraffinic crystal, and this is dense enough to avoid the oxygen quenching, even in the nanocrystal. And crystallinity was well maintained in the nanocrystal, so as the electron polarization. So then we apply the Triplet DNP process, and we could observe nicely the enhancement after the Triplet DNP of 60 seconds. And we could see the broad signal coming from the nanocrystal. And the enhancement factor was about 360 times. So it's about 3 times lower than the bulk powder, but still it's kind of encouraging first example. So it's the first example of Triplet DNP in water, and also first example of Triplet DNP of the nanocrystals. But I should mention that this water signal here, you can see the very sharp signal. This is coming from the water, and this water signal was unfortunately not enhanced. So obviously, now we are trying to transfer the polarization from the nanocrystal to water by changing the sample conditions. Okay, so now I want to change the topic to the polarizing agent. So here I summarized the brief history of Triplet DNP. So after the first room temperature efficient Triplet DNP in 1990, so people optimized the system and introduced different hosts, we introduced the MOF. So from here, you may notice that actually the pentasane and its derivative has been the only polarizing agent. And actually MOF is a bit exceptional, but in other cases, you can see only the host crystals are only limited to this type of the molecular crystal because they can accommodate the pentasane without aggregation. So like 2 naphthalene or 1 tafenyl or 2 benzoic acid can be substituted with pentasane so that you can disperse them. So, but I should mention this Negoro's very nice work. So Negoro and coworkers reported the actual dissolution Triplet DNP. So they applied the Triplet DNP and they dissolve into water, and they could nicely observe the highly enhanced proton signal of this benzoic acid. And later, Kagawa and coworkers introduced this carbon-13 labeled benzoic acid and bring it to the high field, and they could observe the very nice enhanced carbon-13 signal after dissolution. So very nice. But I should point out that the benzoic acid is very special molecule because this dimer have the same size and shape with the pentasane. So the pentasane can be dispersed. But you cannot use the other different, biologically relevant compounds or water because pentasane cannot be dispersed. And another problem of pentasane is the very poor air stability. So if you start working with pentasane, you will hate it. So here shows that the pentasane, if you put the pentasane into THF, and if you go to the restroom and come back, and they all die. So they die within a few minutes by basically the photooxidation in the ambient condition. So to solve these issues, we developed the non-pentasane polarizing agent for the first time. So our approach is very simple. We introduced the electron withdrawing diaz substitution to avoid the photooxidation reaction. So we made this diazepentacene and diazetetrosane. And from the DFT calculation, but this diaz substitution decreased both of the HOMO and LUMO energy levels. So that this should help to suppress the photooxidation and also reaction with singlet oxygen. So as expected from this DFT calculation, we observed a very nice enhancement of the stability in air. So pentacene died within 5 minutes, but diazepentacene can stay over days. A similar trend was observed between the tetracene and the tetracene. So now the air stability issue is becomes much better. And the polarization was also okay. It's a little bit decreased compared with pentacene, but still it's high, about 50% or so. And the polarization lifetime, but it was actually a bit short, like about 3 microseconds. So in the beginning, we thought that, oh, maybe it's too short. But anyway, let's try. Because people believe that 10 microseconds is necessary, but we just tried. And then actually we observed almost similar proton polarization in the paratophenyl system between the pentacene and this diazepentacene. So that actually 3 microseconds was actually not too short. And it's long enough for the polarization transfer. So this is the first example of air stable and high performance polarizing agent. So this is still in the paratophenyl molecular crystal, so you don't need the air stability, but we extend it to the aqueous system. So we developed the first water-soluble polarizing agent based on our diazotetracene. So we modify now the carboxylate moieties. And so here, this is the water-soluble and also air-stable polarizing agent. And to demonstrate this potential, we try to hyperpolarize the crystalline ice. So why crystalline ice? Because the crystalline ice, the T1 is the kind of long, like minutes in the moderate temperature. But if you use the glassy ice, glassy water, you know that the T1 is very short, like seconds. So we try to dope our compound into ice. So here's the actually the molecularly dispersed state of this compound in DMSO at room temperature. But unfortunately, this compound can be dissolved in the sodium salt. It can be dissolved in water, but it's actually aggregate in ice. So you see the shift of fluorescence spectrum, and also you cannot see any EPL signal from this sample. So this compound aggregate. So actually we were very disappointed and almost we were giving up. But my student, Hironori, was smart enough to solve this problem. So he actually made an ion complex with this bulky countercation. And this complex now can be dispersed nicely in ice. So this fluorescence spectrum almost did not any shift. And we could see nice EPL signal. Okay, now we have the polarization, then transfer. Let's transfer to the ice. So then actually we could observe this nice long build-up curve. So, and the build-up constant is about 12 minutes. So it's actually coming, the build-up is happening in crystalline ice. So this is the first example of triplet DNP of pure water in the ice form. But again, I should say that this enhancement is really moderate. I should say it's low. So this is partly because the intersystem crossing quantum is not high in this situation. And also we suspect that there are many, a lot of polarization loss of the glassy ice surrounding the thick glassy ice surrounding the polarizing agent. So now we are trying to solve these issues. But anyway, this is kind of encouraging first example. Okay, so today I introduced our recent works on the nanomaterial and the water-soluble polarizing agent. And our next step is the transfer, the polarization transfer to biological compounds and water, and also increase the enhancement toward our goal of the continuous triplet DNP and in vivo triplet DNP. Okay, and that's it. So thank you for your kind attention.
Okay, thank you very much, Nobu, for your very, very interesting talk. And then like this sounds very promising. And while looking at the Q&A, I already have like quite a lot of questions. So Nobu, can you see the Q&A questions?
Sure. Yeah, now I can open it.
You can see it. Okay.
Yeah.
So like I will just go through the first question. This is also like the kind of question that a lot of people are interested in. I was also asking this myself. What are the prospects of taking triplet DNP to higher static magnetic field? I think you get this all the time. And he assumed like the key limitation is higher power, novel integrated solid effect. But is there anything else in the triplet mechanism that you would think that it would not work at higher field? Because you did this at I saw like 17.7 gigahertz, which is like 0.6 Tesla or 0.7 Tesla. So have you tried it at higher magnetic field, Q band 1.2 or higher? Because like I think the EPR spectrum is also broadened by, you said, hyperfine and zero field splitting.
Right. So
yeah.
Okay, yeah, that's the thank you for the good question. And yeah, that's, I think many audience in this solid state NMR community is very interested in this. So so in short, it's not easy, I think, because you need to satisfy the Hartmann-Hahn condition for the very quick polarization transfer, so that you need a very high power microwave. And also we use the resonator, so it works in this magnetic field, but I think it's not easy at the very high field. So we discussed about this with some colleagues, and but if you can, of course, have nice coherent transfer, so that should also work for the triplet for the very short polarization transfer within microseconds. And maybe another different direction is that like recently, like M3 group also reported nice polarization transfer to the triplet, from the triplet to the radical. And that's maybe one another very good strategy that you don't need to directly use the triplet in that case, so you can increase the polarization of the radical. So, but of course you need a very nice control of the dynamics. But if you can do that, that should be very useful at high field.
Okay, because if I'm not mistaken, like I see here you're using 10 watt, but actually like in our group, we also did like, Bob, maybe you can comment on this. We did like, or at least like Cody did like the ISE or stretch solid effect at 3.35 Tesla W band, because like they have a 1 kilowatt microwave power at Tallahassee. Bob, would you like to comment on the prospects of doing?
Well, no, I mean, that's yeah. We tried to do the integrated solid effect, but at high field, you can't sweep the magnetic field so easily like what you've done here over plus or minus 30 millitesla or so, 30 Gauss. So we were actually sweeping the frequency of the microwave source. So rather than having a constant amplitude, we swept it. And it turns out you see another effect, which we named the stretched solid effect, which actually gives you larger enhancements than the integrated solid effect. I think that's what Kong is referring to.
Exactly. And this like all this is coherent transfer, and everything happens within less than 10 microseconds or something like that.
Yeah, so that would be a possibility with your photo-excited triplets, if you could actually sweep the microwave field rather than using Tom Vinkenbach's magnetic field sweep.
Right.
So you can do that with an AWG, an arbitrary waveform generator. Yeah. But this is very exciting. I mean, it's very nice to see these triplet states being actively used, for DNP, and it would be nice to get them up. So the question though is can you take the triplets to high field? So it's a dipole coupling, so that's not going to be field dependent, but you would start to see a G anisotropy that could be fairly large in these things. Has anybody looked at the G tensors at these triplet states at high field?
Maybe, but I don't have I don't know about it, but yeah, I know to the lower field, at zero field, it doesn't change, but at high field, actually, I have no information. I need to check it out. Yeah, right. But But I agree that if it works, that would be great. AWG if it works,
Yeah.
All right. So thanks for the comment. I mean, like maybe we should move on because there are too many. There are 12 questions. I mean, everyone also asked a similar question. Can this be combined with magic angle spinning?
Oh, right. Right. That's also another interesting point. And of course, this dipolar coupling is too strong, so you cannot average out. So, but so we need maybe some trick to match with the proton Raman frequency, so that recently we start to discuss. So actually we thought about it, but it's not easy to judge whether it works or not. So we are now asking some colleagues to simulate at the magic angle spinning condition that whether it works. So I hope it works, but at this moment I don't have more information about it. Yeah.
All right. Bob can also say we have magic angle spinning EPR probe, right, Bob?
Well, it's not a functional probe. Yeah.
It will be. Yeah. All right. So next question. How would you make sure that the ball milling of nanocrystals did not produce any radicals? Do you do EPR after ball milling as a control experiment, or does the EPR spectrum looks similar before and after ball milling?
Actually, we only see the triplet signal, and we didn't see the signal of the radical. So, right. So, well, maybe there is a possibility of forming the radical, but I think it's small.
And if you don't shine the laser and you do an EPR spectrum, do you see anything?
Actually, we didn't that way. So,
okay.
Yeah.
All right. Next question from Zehong. Would it be possible to put pentacene and other kind of radicals together to do a cross effect DNP?
Right. Right. So that's exactly we are discussing with some people in this solid state NMR community. So but we learned from the literature that we need I'm not sure that the randomly distributing the triplet and the radical works. So maybe we need to by radical, maybe we need to control the distance and coupling.
Yeah.
But
so actually Bob and Andy Smith or beyond constellations, if I'm not mistaken. So what we have tried in our group in the past is to just put a simple mixture of two monoradicals together, and then by random distribution it actually worked. So I think when we put BDPA and tempo, so you have one narrow and a broad one. So this will work. I mean, Bob can also comment if you want. Yeah, but this is a nice
No, it was tridal tempo because tridal is water soluble. This was in glycerol water.
Okay. Yeah.
Yeah.
So ideally, you want one narrow line and one broad line.
Right. But at least I should say that now we have the water-soluble, polarizing agent. So now we can, disperse into some like a grass matrix, because pentacene is previously people only use pentacene, and pentacene severely strongly aggregate in many matrix. So maybe it was difficult, but now we can try.
Yeah, put pentacene and tridal, and then do a field profile, and magic angle spinning, of course, which is important for cross effect. Everything. So next question from Michael Hope: have you done any microscopy on the pentacene derivatives in crystalline ice? It thinks that you will form agglomerates outside the crystals, even if the protective bulk cannot means the young question. We should explain.
Right. We haven't tried because of the strong scattering of the ice, but from our eye, it's the color change a lot. So it's clear even to our eye that they aggregate in ice, but in the ion complex we start hydrophilic big counter cation. That kind of aggregation didn't happen. But actually, I should mention one interesting point. That's the a bit tricky part, but so this actually compound can be dispersed in crystalline ice, but not in water. So actually hydrophilicity is not still enough. So, but during the crystallization of water, the polarizing agent kind of dispersed. So we are very much surprised, but from this we suspect that still this looks dispersed, but maybe it forms still somehow like a nano domain of the this polarizing agent rich domain. So is still, I think, the remaining the problem. So we are trying to optimize more the chemical structure to have better the dispersibility. Yeah.
Okay, actually, and then due to time constraint, I will probably take a few, one or two more questions. Actually, like what you just told us is actually related to what I see. Christian Grissinger, okay. She also asked, what's the reason that you do not observe the DNP to water DNP to water transfer in the pentacene nanocrystals? Is the water excluded and therefore it's not close to the site of the triplet electrons? So, right. Yeah, what would the exclusion of oxygen also lead to exclusion of water?
Okay, so yeah. Yeah, thank you for the question. And we really want to transfer. So, and so we think that, okay, so I should show the structure of the surfactant. So we think that this surfactant is kind of blocking the polarization transfer. So this actually T1 is very short. So our guess is that this kind of making the barrier for the polarization diffusion from the crystal to water. So now we are changing this. We are synthesizing our kind of original surfactant to control the interface structure to allow the polarization transfer. And exclusion of oxygen is a different issue. So the oxygen, both of oxygen and water may come close to the the nanocrystal, but both of oxygen and water don't need to come in, so they don't come in. So that's good for blocking the oxygen, and actually, and the proton can the diffuse the nuclear polarization of proton can diffuse and then come to the interface. So water don't need to come in, so proton polarization can diffuse and come out. So that's our kind of expected scenario. Yeah.
Okay. There are quite many questions, and then oh, maybe I just take one random question from Yifan. Have you tried to test shorter aromatic molecules and derivatives that might be easier to incorporate with other host materials? Or, is there any other magic compound rather than the pentacene-like molecule? Is right. There only one magic molecule? And have you explored other kind of agents?
Right. Actually, in the beginning, we saw that pentacene is perfect, and the air stability is only the issue. And later we learned from this diazepentacene work, actually many compounds can give you the high polarization, but actually most of them have the very short polarization lifetime. That's the problem. So you can take one small compound, actually polarization is good, but most of case polarization lifetime is short. But so shorter than 10 microseconds, and then usually I think people did not care about that kind of compound. Okay, maybe it's too short. But actually, we found that the 3 microseconds is okay. So actually, this really expands the candidates. So based on this work, we now trying the different polarizing agent. So now we don't need to stick to these async compounds. There are many other compounds can produce the triplet state and also polarize the triplet state. So now I think it's very interesting to try the different polarizing agent, right? And now we are also expecting some magic, very super polarizing agent to come out. Yeah.
Yeah. Maybe I'm just curious. I know the polarization lifetime is solved in this order, but how about the triplet state lifetime? Is it always are you always limited to the 1 kilohertz repetition rate? Can you go higher, or does that vary from compound to compound? Because if the lifetime is short, it's okay. If you can regenerate it fast enough, that can somehow compensate.
Right, that's true. So So 1 kilohertz repetition is now limited by the triplet lifetime of the pentacene. And basically, we only need like at most 10 microseconds for the polarization transfer. So triplet lifetime is not necessary to be longer than that. So, of course, triplet lifetime can vary a lot from like a nanosecond or to the millisecond. So we can choose some good compound with, but we should also be careful about the intersystem crossing efficiency. So that so we need to balance all the basically the intersystem crossing efficiency and also the polarization and this polarization lifetime and the triplet lifetime. So intersystem crossing should be efficient, polarization should be high, polarization lifetime should be long enough, but not necessary to be very long. And also the triplet lifetime should not be too long. So it should be like a at the most like a 20 microsecond or something like that. It should not be like 1 millisecond or so. That's the basic parameters we should define. And then now we are trying to find a better candidate. Yeah.
All right. Due to time constraint, like I'm afraid that I cannot like take more questions, but I will put all this Q&A on the Dropbox, right. And if you're free, like you can comment on it. Right. But thanks for your comment on this, like the lifetime, polarization lifetime, ISC crossing, and like I hope you can, with your morph chemistry and your synthesis, you can like find out a periodic table of all different kind of magic compounds that we are looking forward to see this in the future. Thank you very much, and good night. Thanks for doing this, even though I know this is like almost like 1 o'clock in Japan. So good night and thank you. It's a very, very nice talk. I will now pass the session to Bob.
Okay, so our second speaker today is Frederick Blanc, and he's from the home of the Beatles, Liverpool in the UK. And he's going to tell us about zeolite heterogeneous catalysis taught in